Hello and welcome to this lecture on advanced electric drives. In the last lecture, we are discussing about the director control of induction motor drive when fed from a 3-level inverter. Now, when we have a 3-level inverter, we can apply this for high power application. By high power application, we mean beyond 1 megawatt. So, when you have a large induction motor drive, and usually for large drive, the voltage rating of the motor is also high. So, we can think of a multi-level inverter feeding an induction motor drive. And we selected a diode clamp multi-level inverter for controlling the induction motor. And one of the popular methods of control is the director control. This is what we are discussing in the last lecture, that in director control, the torque equation is given in a very simplified form. It is basically proportional to the product of two fluxes, the stator flux Is, the rotor flux Ir, that we were discussing in the last lecture, that Te is equal to the constant 3 by 2 into P by 2, Lm by sigma Ls into Lr, and then psi s is the amplitude of the stator flux, psi r is the amplitude of the rotor flux, then sin gamma SR. This gamma SR is the angle between the two fluxes, this angle. So, we have the stator flux is psi s, the rotor flux is psi r, the flux vectors, and then gamma SR is the angle between the two fluxes, this angle. So, what we can do here, we can control the torque by controlling gamma SR. Gamma SR is the angle between the two fluxes. So, we can have a direct control over the stator flux by applying the various voltage vectors. Now, we have seen that in the last lecture that in a 3-level inverter we have got 27 possible voltage vectors. So, we have more flexibility. So, we can apply one of these voltage vectors to control the stator flux in an induction motor. So, when we apply a voltage vector, the flux will change as per this equation. So, we have psi s, the change in the flux is a vector, and if we ignore the resistance drop is Is into Rs. This is applied voltage Vs, voltage vector Vs minus Is into Rs into delta t is the time interval. So, what we finally obtain is Vs into delta t, and we know that the stator flux, the initial value is psi s naught, and we have a change in the value, that is delta psi s. So, if you add this vectorially, what we obtain is the total flux vector, that is psi s. So, this is basically a vector triangle. So, one side is psi s naught and the other side is delta psi s, and the third side is psi s. So, these are the three sides, and by applying a voltage vector, that is Vs, we can control the stator flux effectively. Now, we can find out the magnitude of the various fluxes, psi ds and psi qs. So, we have, this is our d axis and this one is the q axis, d and q axis respectively. The stator flux vector psi s can be resolved into two different components, and one component is along the d axis, and we call that to be psi ds, and the other component is along the q axis, and we call that to be psi qs. So, we have two components of the stator flux linkages, and we can find out this angle theta s. This is the angle theta s that we discussed in the last lecture. This is angle So, this angle theta s is given as tan inverse of psi qs by psi ds. So, we have this angle theta s is tan inverse of psi qs. So, psi qs is the q axis flux and psi ds is the d axis flux. So, if we take, this is basically an orthogonal axis, d and q axis are perpendicular to each other. So, if we take the inverse of this tan inverse of psi qs by psi ds, we get theta s. So, the theta s will help us locate the flux in various sectors. So, we have seen that we have 6 different sectors from 1 to 6 that we have already seen in the last lecture. These are the various sectors: sector 1, sector 2, between this, and each one is 60-degree interval, sector 3, sector 4, sector 5 and sector 6. So, we have 6 different sectors and the flux vector can lie in any one of the 6 sectors, and that can be found out by calculating theta s. So, theta s will help us know the position of the stator flux vector, and hence we can find out which vector can be applied so that we control the flux and the torque respectively. So, if we see this in the form of block diagram, this is actually our 3-level inverter. We are feeding a induction motor in this case, and we have 3 different legs here: phase A, phase B and phase C, and these are the various diodes, the feedback diodes and the clamping diodes, and these are clamped to the midpoint of the input voltage, in this case VDC by 2 and VDC by 2, the total being VDC. The total voltage here, the DC voltage here is VDC, and the voltage drop across C1 and C2, each capacitor is VDC by 2. And then these are the flux vectors. The stator flux is psi s and the rotor flux is psi r, and then we can calculate the torque in this case, 3 by 2 into p by 2, we have a constant here, lambda and the psi are the same, the flux, the stator flux into the rotor flux into the sine of the angle between them, gamma SR, and gamma SR is the angle between psi s and psi r. So, the torque can be controlled by varying lambda s is same as psi s and lambda r is same as psi r. So, we can vary this torque either by varying lambda s, lambda r, or by varying gamma SR. Now, we know that flux variation is not preferred, because if we vary the flux, there will be a delay associated with the flux change. Furthermore, a variable flux machine is not very attractive. If we increase the flux, the machine may saturate. If we decrease the flux, the machine may underflux. So, the saturated machine will have higher core loss, and if the flux is reduced, the power level also will reduce. So, the first reason is that the flux change will accompany or will be accompanied by a delay, and secondly, a machine with variable flux may sometimes saturate and may lead to higher core loss. So, what we do, we control the torque by controlling gamma SR, the angle between the 2 fluxes. This is the angle, and what we obtain finally is a closed loop block diagram of speed control. So, we have the induction motor here, and we have a speed sensor. The speed sensor gives us the speed, and what we get here is actual speed. It is fed back here, and we have a reference speed, that is omega r star, and we compare the actual speed with the reference speed and then feed it to a speed controller or PI controller, Kp plus Ki by S. and then we have a limiter, because this PI controller can sometimes integrate the error which may reach a very high value. So, to limit the torque to a practical limit, what we do, we limit the torque to a positive limit and a negative limit. Obviously, in a machine we will have a maximum possible torque, because torque and the currents are related. So, we limit the torque to a maximum limit and a minimum limit, and hence we need a limiter. And then this limiter will limit the value of the torque, and it gives basically the torque reference. If the value is in between this limit, whatever is the output of the speed controller will be the torque, and if it is higher than the positive limit, the torque will be limited to the positive value, and if it is lower than the negative limit, basically for the braking operation or for negative speed, again the value of the torque will be limited to the negative maximum value. So, the speed controller gives the torque reference. So, this torque reference TE star is compared with the actual torque, and the actual torque is obtained from a torque and flux estimator. So, how can we estimate the torque and flux? We will see it later. And this feeds to a torque comparator, a hysteresis comparator. So, if this actual torque is not same as the reference torque, we get an error, and this is processed to a hysteresis comparator. This will be giving us the torque status, as you have in case of a DTC of a 2-level induction motor drive. And we have the reference flux here, lambda star, and that is compared with the actual flux lambda, and it is fed to a flux comparator. So, we have a torque comparator and a flux comparator, and the sector information is also obtained by finding out psi ds and psi qs. So, we know in which sector the stator flux is lying, whether in 1, 2 or 6. So, we can find out the sector information, and by sector information we can know which vector should be applied to the induction motor, because we have various voltage vectors. So, they will vary depending upon the various sectors. The sector information will help us apply the appropriate voltage vector to the induction motor. So, this is what we have here, and then the output of this is the voltage vector, and when we know the voltage vector, we can find out the switching signals. We have in fact a 3-level inverter, and in a 3-level inverter what we have here is we have 12 possible switches. Per phase we have 1, 2, 3 and 4. This is for phase A, and similarly for phase B we have again 4 switches. Phase C also we have 4 switches. So, in total we have got 12 switches. So, this information, or this phase, per phase we have got 4 switching signals. These are the switching signals for phase A 4, phase B 4 and phase C 4. And the switching signals are fed to the diode clamped multi-level inverter, 3-phase inverter, and what we obtain is the output voltage for phase A, phase B and phase C. And these voltages will pass some current. We have the induction motor here, and we take this feedback of the voltages and the currents. We have the current sensor here and we have the voltage sensors here. So, we can take this information to the torque and flux estimator, which will give us the flux magnitude for the feedback. This is basically the calculated value of flux, the torque magnitude for feedback, the torque of the motor, and the sector information about the stator flux, psi s or lambda s. So, we will see how this flux and torque estimator estimates the flux and the torque respectively. Now we know that flux psi s or lambda s has got two components, lambda ds and lambda qs. So we can calculate the various components in the following fashion. This has got two components, lambda ds and lambda qs. So we can integrate the corresponding voltages VDS minus RS IDS. So this VDS is basically the direct axis voltage in the stationary reference frame. RS into IDS is the resistance drop. We can measure the current by Hall sensor. In fact, what we are doing here, we are measuring not VDS, VQS, we are measuring VA, VB and VC. Now when we are measuring VA, VB and VC, we can transform them into dq by a mere stationary transformation, because this lambda ds and lambda qs are the flux linkages in the d and q axis in the stationary reference frame. Similarly, we can have sensors to measure IA, IB and IC, and we can transform this IA, IB, IC into IDS and IQS by a stationary transformation. So in this equation we know VDS, we know IDS and we know VQS, also we know IQS. We can calculate these two flux components psi ds and psi qs, or lambda ds and lambda qs. So lambda s is the total flux, that is equal to under root psi ds square plus psi qs square, and theta s is obtained by tan inverse of lambda qs by lambda ds. And the torque, once we know this corresponding fluxes lambda ds and lambda qs, we can calculate the torque by this equation 3p by 4. P is the number of poles, 3p by 4 into IQS into lambda ds minus IDS into lambda qs. So we can find out the magnitude of the flux linkage, that is lambda s, also the magnitude of the torque. So these are basically used for feeding back the values for control. We have a flux controller, we also have a torque controller. So we compare the reference values with the actual values, and the actual values are estimated using the estimator. And from theta s we can find out in which sector the flux vector is lying. So if we try to see the various voltage vectors, this is a recapitulation of what we have done in the last lecture. So we have in fact we have 27 possible combinations, and we have in fact the full vector V1f and V1h. Similarly, we have V2f the full vector, and V2h is the half vector, and V3f and V3h, and V4f and V4h. Similarly, we have V5f and V5h, and V6f and V6h. So we have 6 different main vectors and half vectors, and in between we have intermediate voltage vectors. For example, we have here V1i, the intermediate voltage vector, and V2i, V3i, V4i, V5i and V6i. So when we control the flux lambda s can be anywhere here. And what are the various sectors that we have already discussed? That this is the sector 1, then we have sector 2 here, sector 3 between these two, 2i and 3i, and then sector 4 between 3i and 4i, sector 5 between 4i and 5i, and sector 6 between 5i and 6i. So we have basically 6 sectors here, and since we have a 3-level inverter, we have got the band the torque band is divided into 4 zones. The lower positive torque band, the upper positive torque band, and the lower negative torque band and upper negative torque band. So, we can see here that we have upper torque band here. This is basically the reference torque shown here, and then we have the various torque bands in this case. This is the upper torque band, and this one is the lower torque band, and then we have a negative lower torque band and negative upper torque band. Now, if we go for the control of a 3-level inverter, just like a 2-level inverter, we can also have a direct torque control, but in that case we will be switching this 3-level inverter as a 2-level inverter. We won't have the full advantage of the 3-level inverter. The flexibility that it offers, having so many different voltage vectors, cannot be exploited. So, if we go for a 2-level switching, we will be basically switching from low to upper like this. So, this is basically a 2-level torque slope here. So, we apply a full voltage vector from negative band to the positive band, it increases like this, and then we apply full voltage vector in the other direction, it goes down. So, this basically is the switching. So, this is one way. So, in this case, you know that we have got higher torque ripples. So, instead of that, what we do in this case is, when it reaches the upper band, instead of a full voltage vector, we apply a half voltage vector. So, that basically reduces the slope of the torque, and hence we have a smoother operation. So, here what we have in this case is this, that from the negative upper band to the lower band, positive lower band, this basically the torque need to be increased. So, we have increased the torque here, and then when it crosses the lower torque band, the torque need not be increased with that rate. So, what we do here, we replace the full voltage vector by a half voltage vector, and thus the slope is reduced in this case. And when it touches the upper torque band, what we do here, instead of applying a full voltage vector, we apply a 0 voltage vector. So, when we apply a 0 voltage vector, the torque decreases, and then here we apply again a full voltage vector, and when it reaches the lower torque band, the full vector is replaced by a half vector. So, basically we can see that the switching frequency is also reduced here, and also the rate of change of the torque is also very less, and hence the motor responds better to this kind of waveform. So, if we see in the form of a table, so what we have drawn here is lambda s in sector K. So, we have so many sectors in this case. So, this is basically first sector, sector 1, sector 2, 3, 4, 5 and 6. So, if it is in sector K, when we want to increase the flux and increase the torque, so torque can be increased or increased with more value. So, this is basically when you have a small arrow here, it is just increase, and when you have a large arrow, this is more increase. So, let us see that we want to increase the flux and increase the torque. So, if you want to increase the flux and increase the torque, and we are in sector 1, 1 is basically this sector, from this to this, we apply Vk plus 1 half voltage vector. So, Vk plus 1 is, Vk is 1 here, k plus 1 is 2. So, basically here we apply 2h. So, when we are in sector 1 and we want to increase the flux and the torque simultaneously, and torque increase is not that fast, so we apply V 2h, 2 half vector. Half vector means here this is the full vector, so we apply the half vector V2h. The flux will increase in this case V2f. So it increases not with that fast, it basically increases slowly. And then if we want to increase the flux but increase torque more, we apply the full voltage vector Vk plus 1f. So we can apply V full here. And in this case, if you want to decrease the torque, we apply Vz, the 0 voltage vector. So when you apply a 0 voltage vector, the torque reduces. So the voltage goes down here. I mean the torque goes down. Similarly, we can think of a situation where we want to reduce the flux. Now if the flux is reduced, we want to reduce the flux but increase the torque. Second situation here. So we want to reduce the torque but reduce the flux but increase the torque. We will have Vk plus 2h. What is k plus 2? K is 1 here, 1 plus 2 is 3. So here we can apply a voltage vector like this. So if we apply a voltage vector like this, 3f here, so this 3f will reduce the flux. The flux is reduced because it is demagnetizing the flux, lambda s. And if we want to increase the torque more, instead of a full vector half vector, we apply full vector. And then if we want to decrease the flux and also decrease the torque, it is Vk minus 2h. So k minus 2, k is 1 here, k minus 2 is 4h. So what is 4 here? So in this case 4 is this vector. This is 4. So in this case, if you want to increase 5, so if you want to decrease the flux and decrease the torque, we apply 5h. So what we do here, we apply 5h here. So if you apply 5h, both the flux and the torque will reduce corresponding to this situation. So what we see here, that when we have a multi-level inverter, in this case the example has been shown for a 3-level inverter, we have more flexibility, and more flexibility will result in less switching. The switching frequency will go down and will have better torque response because the torque ripple can be reduced using a 3-level inverter. So, and this is also applied for very high power application. And in high power, we don't go for very high switching frequency. The switching frequency should be as low as possible. So this is basically the director control of an induction motor fed from a 3-level inverter. Now we will see some classification of induction motors. Induction motors are called the workhorse of industry. We can have large specification of induction motors. However, we can classify them into various class, like class A, B, C, D and so on. This has been done by NEMA, and this NEMA classification help us choose this induction motor for a very specific application. Now we will see some classification of induction motors. So we will be discussing about classifications of induction motor, and this is as per NEMA standard. What does this NEMA stand for National Electrical Manufacturers Association. Now, in this case we can classify the induction motors in various categories, and these are suited for some specific application. We will start with class B. Now, class B induction motor is basically a normal motor having normal torque and normal slip. They can be used for very general application. We start with class B. Now, class B has got normal torque, normal slip, and normal logged ampere. And the full load slip is less than 0.04. So, this is basically the specification of class B motors: normal torque, normal logged ampere or the starting current, it takes normal starting current, and the full load slip is usually less than 4%. Now, if we draw the torque speed characteristic of this motor, it basically is a normal torque speed characteristic and has got very general application. So, let us see the torque speed characteristic of class B motor. So, we have torque speed characteristic like this. This is the torque, and we have the speed in the y axis, and the torque speed characteristic is a normal torque speed characteristic. So, we have the maximum torque here, and this is the starting torque. The starting torque is not very high, but it is moderate, and this has got normal rotor resistance. The rotor resistance is not very low, neither it is very high. Now, if you want to have very high torque and very high efficiency, it may not be possible to have using class B motors. Class B motors are normal motors. Now, if somebody wants to have a very high torque means in the full load condition the torque should be very high. So, if one wants to have a very high torque, the torque can be increased by reducing the rotor resistance. If you reduce the rotor resistance and also reduce the rotor inductance, the leakage inductance, torque can be increased. So, class A motors have got high torque and low slip. The slip is low and hence the efficiency is better. So, we will see the specification of class A motors. So, we have class A motors. So, we have high torque, low slip, high logged ampere, or very high starting current. So, the torque speed characteristic can be given like this. So, we have the speed here and we have the torque in the x axis. So, this is basically class A motor. Now, if we compare this with class B, the class B will be like this. So, this is class A, and this one is class B. So, if we compare these two motors, we see that the class B has got higher torque, and of course, if how is the torque made higher? The torque is made higher by reducing the leakage inductance and by reducing the rotor resistance, and the slip is also reduced. The slip, the full load slip in this case is less than 1%. So, we can see here that the full load slip here is less than 1%, and that is possible if we can reduce the rotor resistance, and if the slip is reduced, the losses are also reduced, because if the motor operates at a reduced slip, the rotor copper loss is reduced, and hence the efficiency of this kind of motors are high. Now, we have seen actually class B and class A motors, and we understand that class A motors have got low rotor resistance, and hence that has got higher torque, but unfortunately the starting torque is low, because if the rotor resistance is low, the starting torque of class A motors are low. So, we can see that by means of the speed torque characteristic, we observe here that the starting torque of class A motors are smaller compared to that of class B, and even class B motors are also having low starting torque. Now, if a specification or if a application demands that we should have a higher starting torque, we should have a motor with higher starting torque, and the application also demands that the running torque should also be quite high. So, we have two conditions or two specifications, that we should have higher starting torque as well as higher running torque. So, if we have both the requirement of higher starting torque and higher running torque, we go for class C motors. In fact, class C motors are manufactured in a little different way. The rotors are not usual rotors, they are double cage or deep bar rotors. So, we will see the characteristic of class C motors. So, in class C what we have? We have high torques and normal slip, and we have normal logged ampere. And high torque and normal slip and normal logged ampere. So, we can draw the torque speed characteristic. So, this is the speed and the torque here. So, we can also say high starting torque, high torques, high starting torque. So, in this case the torque speed characteristic will be like this. We have reasonably high starting torque, may not be very high, but it is high starting torque, and we also have normal slip. The slip is normal slip about 4 to 5% full load slip, but the starting torque is quite high, and even in the running condition the torque is quite significant. So, here what we use in this case is a double cage rotor. So, these motors have got two cages in the rotor, one is the upper cage and the other is the lower cage, and this combination of the two cages help obtain higher starting torque as well as higher running torque. So, we have double cage rotor, double cage rotor construction or deep bar rotor. construction. And these are recommended for load requiring high starting torque. Recommended for applications requiring high starting torque. And then we have another class of motor called class D motor. Class D motors have got a very high rotor resistance. When the rotor resistance is increased, naturally the logged ampere is reduced or the starting current is reduced. There are so many applications which require frequent starts and stops. Say for example, the punching machine, the press. Now when we think about this kind of motors or this kind of machines, they require frequent start and stops. Now if a machine has got large starting current, there will be voltage dip and frequent start and stops may not be acceptable. So this class of motors, which are class D motors, have got large rotor resistance and hence the starting current is quite low. On the other hand, the starting torque is quite significant because of higher starting power factor, and hence this class of motors are employed in loads like punching machines and press and things like that. So in class D motors, we will see now the class D motors. So what we have here, we have high starting torque and high slip. Naturally this has got high slip. The slip will be high here, and low starting current. Same as low logged amperes. So if we see the characteristic of this class of motors, we will have the torque speed characteristic like this. This is omega m here, and we have the torque in this case. And here what we have in this case is that we have high starting torque, but we have high slip as well. The full load slip is quite large. This is the full load slip. So the full load slip varies between 5% to 13%, and the starting torque could be 275 to 300% of full load torque. So this class of motors are applied with punch presses, applications. So this is basically class D motor having large rotor resistance, and they are applied in those applications where we require high starting torque. Now these are the classification of the induction motors. Now when we go to manufacture an induction motor, we can manufacture either a normal induction motor or a high efficient induction motor. By high efficient induction motor we mean special consideration have been taken to maximize the efficiency of the motor. And how can we maximize the efficiency of the motor. The motors have got various losses, and the various losses are of this percentage. If you take a typical induction motor, the losses will be of this percentage. So, if we see the losses in an induction motor, loss distribution in an induction motor. So, these are the various losses we have. What are the various losses? This is the type of loss, and here we have percentage of total loss. What are the various losses here? We start with the stator copper loss, and this is about 37% of the total loss. And then we talk about the rotor copper loss. Rotor copper loss is about 18%, and the core loss is about 20%, and friction and the windage losses is about 9%. Straight load losses is about 16%. So, these are the various losses of an induction motor. Now, how can we minimize the losses? The loss can be minimized from various aspects. We have the loss in the copper in the stator and the copper in the rotor. Usually, the rotor is made up of aluminum die cast. They pour molten aluminum onto the rotor to manufacture the rotor bars for a squirrel cage induction motor. Now, we can put more copper in the rotor. So, if you have more copper in the rotor, the resistance will be less and the losses will also be less. So, we can maximize the efficiency or minimize the loss in the copper by having copper in the rotor. Also, we have more copper in the stator. That is one aspect. So, one thing is that the rotor bars are made up of copper. So, we can discuss about high efficiency induction motor. So, we can achieve that by minimizing the copper loss, the copper losses by having copper in the rotor. So, if we have copper in the rotor, the losses are also minimized, and hence we have higher efficiency. And then the next loss is basically the core loss. Core loss occurs in the core of the stator, the core of the rotor. So, we can minimize the core loss by having good quality stamping. We can in fact minimize the hysteresis and eddy current loss in the core by having good quality material. So, the material has to be improved to minimize the core loss, and the laminations have to be thinner in size to minimize the core loss. So, minimization of the core loss by having better quality laminations. So, minimizing the core loss by having better quality laminations in the core. And of course, the friction and the windage losses are a part of the machine that cannot be reduced significantly. The friction will anyway be there, the windage losses will be there. So, if we have reduced losses, sometimes the motor is equipped with extra cooling fans. So, if the losses are minimized, the cooling fan can be dispensed with. If the cooling fan is removed or is not available with the motor, the windage losses will also be reduced. So, we can reduce the windage losses by having reduced core loss and reduced copper loss, thereby dispensing the need of having a extra cooling fan. And then the strain load losses of course is not measurable, is not attributed to a single factor, and hence that loss will still be there. So, we can reduce the various losses in this case, and hence we have a high efficiency motor. So, this is basically the ways to minimize the losses of the motor and to have better efficiency of induction motor. So, in this lecture we have seen the high power induction motor drives, we have seen the director control of induction motor fed from a 3-level inverter, and the various classifications of induction motors based on NEMA, and we have also seen the loss distribution of induction motors, and also the ways to reduce the losses are also discussed. In the next lecture we will throw some light on the thermal aspect of the motor. The motor has got an electrical aspect, also has a thermal aspect. Now, when we pass current through the windings, there will be losses, and these losses will raise the temperature of the machine. So, we will see how we can find out the temperature rise of the machine by having a thermal model of the overall motor drive system.